the alcohols, we're going to start off by just learning to draw and name them. So this is now 3rd of February 2025, and I need a pen that works.
I'll give you a pen.
Cheers.
You're welcome.
And we're concentrating on the alcohols to start with. I just want you to know a couple of reactions of them as well and how they're formed. So first of all, the functional group that hangs off the alcohols is that OH that we learn in year 12 is called a hydroxyl. So that stuff is meth because it's one carbon, an because there's no double bonds, ol because it's an alcohol, methanol. I'll just draw that again without the brackets around the OH there. So that's methanol. You can write it either with a bond between the O and the H or just like that. Please make sure, just like you did earlier on with the mini whiteboard, that the oxygen is always attached to the carbon. So if I draw it this way, if I draw ethanol with the oxygen pointing upwards, just for no particular reason, make sure the carbon is attached to the oxygen when you're drawing it, please. Doesn't matter what position you put the OH in, as long as the carbon is attached to the oxygen. So that's ethanol, and you can get the idea then that you can have propanol as well. Like so. I think you're only expected to know up to ethanol. You can get the idea that the prop refers to 3 carbons, an because it's because there's no double bonds, ol because it's an alcohol, so propanol. You can have the OH in of the second carbon. That's also another form of propanol. It's a slightly different molecule, but you got the idea.
So what about butanol?
Well, you can. Right, having just checked, you do need to be able to draw butanol as well, but I'm sure you can draw butanol without any particular challenge. 1, 2, 3, 4, O, H, and the 4 hydrogens. That's but, because it's 4 carbons, and because there's no double bond, ol. You could have butenol as well, but the GCSE tend to stick to one group, one functional group. This is a good time for me to teach you the word, or remind you of the word, homologous series. I don't remember whether I told you this term last time. I want to see people nodding. This is a family of organic molecules that differ by CH2, so the chain gets longer each time. So same family, same functional group, differ by CH2, same functional group. And then as you go through the functional, through the series, methanol, ethanol, propanol, butanol, what happens to the boiling points? Do they go up, point up, or down, point down? Yeah, so the boiling points increase as you get a longer chain because you get slightly stronger intermolecular forces each time. Okay. Now you already know a little bit about formation of alcohols. We're going to spend some time on that to start with. And we're going to concentrate specifically on ethanol because that's the one you're expected to know about. And then we'll spend time on the reactions of them. Okay. So there's a couple of ways of making them, one of which you've already seen, and we're going to compare and contrast that with another way of making them. And we did this and practiced this already today, but alcohols can be made from the corresponding alkene in the presence of steam and a catalyst, which is an acid, typically phosphoric acid. And it's an addition reaction where the water adds across the 2 carbons, one of the hydrogens of water on 1 carbon, and the other part of the water, the OH, on the other carbon, right? So we've seen that already. It's an addition reaction, one of the sort of class of addition reactions that alcohols do. And there's some interesting sort of points about that I'll pick up on as well. So the atom economy is a calculation that we had to learn earlier on in the year, which is the mass of all of the products added together, formula mass of all the products added together, the formula mass of all of the desired products added together divided by the formula mass of all of the products added together. Because there's only one product, it means the atom economy is 100%. And so there's no waste product, there's nothing produced that we don't want. You do have to do it at a high temperature. So high energy requirement, therefore. But you do get one pure product. So no purification needed, which might be distillation, for example. Right, so that's a good way of making ethanol. Ethanol's got lots of uses that we'll discuss in a minute. Like we talked about the other day, we said about using it for those hand sanitizers, for example, or as a fuel. Right, so the other way of making alcohols is what I've attempted once in my kitchen to explode. Well, I was tempted twice, once with an explosive outcome, and I'm not going to do it again. But you can make alcohol, as happens very easily, through a process called fermentation, right? So fermentation
Isn't that how moonshine was made?
is how all alcohol is made that's drinkable. But yeah, moonshine is alcohol being made in people's bathtubs, things like that. Yeah, there's a big risks associated with that. Making beer and stuff is quite easy, and people do this. You can do some stuff at home quite safely. But anyway, so you can make alcohol through fermentation. There's some significant differences from the making it through addition reactions, right? So with fermentation, what you're doing is you're taking some sort of ingredient that contains glucose, contains sugars, right? So it might be that you're making alcohol from grapes, which is what wine is, and it's the sugar in the grapes that turns into the alcohol. It might be that you're using malted wheat, which is what you have in beer, and that's when you've got the grain, the sugar is in the grain that you turn into beer. I don't know all that much about beer making, if I'm honest. It might be that you're doing it like the Russians do with potatoes, and there's the sugar in the potatoes that's turned into the alcohol, right? And so you get things like vodka and so on from that. So there's lots of ways of doing that. There's lots of ways of making alcohol from stuff that's got sugar in, but essentially it's always the same reaction. So if we call that fermentation, and the reaction is the sugar, C6H12O6, which is the glucose, and the thing that you need to know is that requires yeast, which is an enzyme, right? I think you know that enzymes are biological catalysts. I'm getting some nods around the room. So yeast is a biological catalyst. So if you leave, if you see it in sort of around here in summer, you see the apples falling on the ground in the orchards. Over a period of time, they'll start to ferment a little bit without adding yeast, and you get supposedly you get wasps and things that have been eating the apples late in the year, been sitting on the ground, and they start to get a bit drunk because of alcohol in them. So it doesn't necessarily need yeast to be added. It might be that there's the alcohol will form naturally given enough time. But if you add yeast, it speeds up this process quite significantly, and what you get is 2 ethanol molecules per molecule of glucose. Let's write that as glucose. But you also get a byproduct which will make a lot of sense when you realise that beer, champagne, things like that are fizzy. The fizz comes from the carbon dioxide that's made in the fermentation process. So that's what makes alcohol drinks fizzy, because the carbon dioxide dissolves a bit, doesn't it, in water, and makes it fizzy. Now that reaction, being a biological catalyst, will be done at a temperature which suits the catalyst best of all, the enzyme best of all. So what temperature do enzymes work best at? Write that on your mini whiteboards.
Can we do a practical in which we ferment alcohol?
Yeah.
We can.
Yeah.
Oh, yippee. Can we drink it?
No, obviously. Yeah, something like that. So around about 40 degrees, loads of you have written sort of 37 degrees, but around about 40 degrees will do for this. Now if we compare and contrast that with the addition, this is a much lower temperature, so that's significantly lower temperature than the addition reaction. So there's a much lower temperature than the addition reaction, which is significant. But one of the issues with fermentation, you might know that some alcohols are produced and can be sold at reasonably high percentages, enough to get you really very drunk very quickly, which is not obviously a good thing. But many alcohols, like beer, typically tops out at about 4 or 5%, and wines tops out at sort of 13-14%, and that's because at higher concentrations of ethanol, the yeast will denature. It actually kind of unfolds and doesn't work anymore. So the highest yield you can get with specialist yeasts is around about 15% yield. And so, though it's a much lower temperature than addition reactions, you only get a 15% yield from it. And so that means you then have to distill if you want to get pure ethanol for burning or using as hand sanitizer. So distillation needed. And distillation, of course, requires energy to be put into it, high temperature. So you need to get this down. These comparisons are classic 6 markers. Right, so distillation needed, that requires energy. So you can compare and contrast. The fermentation requires sugars, and sugars are, of course, sugars are, of course, a product of the plants that we're using, like sugar beet or sugar cane or grapes or grain or whatever else it might be that you're using. And that means that they've come in directly then from photosynthesis, right? Which means they're taking in carbon dioxide from the atmosphere when they're growing, right? So if I just write naturally occurring for now, I'll come back to why that's significant. Naturally, I spelled that wrong. Oh, near enough. Naturally occurring, again, I'm not sure about the spelling there. So naturally occurring from plants, and that's significant, right? So this ingredient, the ethene, is not something that comes from plants. This is something that's produced indirectly from crude oil. So we're going back to that resources topic idea, aren't we, with finite and renewable. So the plants, glucose, ethanol that's made from that is a naturally occurring, renewable form of ethanol, and the addition reaction from ethene comes in directly from crude oil, which has been cracked. Right? Can you see that there's significant differences between them? So, and we're also seeing the strengths and weaknesses of either method. So one is requires high temperatures for distillation, one requires high temperatures for doing the reaction. One you do at low temperature, one gets a much higher yield and atom economy, one is a finite resource, one is a renewable resource, one takes carbon dioxide out of the atmosphere through photosynthesis, and one doesn't. right? That's significant. So let's think about the uses and reactions of alcohol or ethanol now. Right, so the uses of them, first of all, I think it's fair to say that we use it in drinking, but this is not something I would focus on in an exam. So we all know that ethanol is found in alcoholic drinks, but that's not something that you're going to be writing about, right? You can also use it as a fuel. So biodiesel contains about 5 or 10% ethanol, which has come from fermented crops. So specifically, it is a biofuel, and biofuels, remember, remove CO2 from atmosphere when growing, when the plant is growing through photosynthesis. And if you don't know the reaction of photosynthesis, I suggest you try to learn it. And when you burn the biofuel, you do still release carbon dioxide, but overall we say that it's carbon neutral. So CO2 is released when you burn. Some people think, in fact most of my year 13s in their mock this week thought that CO2 is not released from biofuels. Of course it is. You burn ethanol, you get carbon dioxide and water like any other organic molecule, but it's just that carbon dioxide is removed from the atmosphere when the plant's growing, so CO2 still released when burning, but removed during growing. So it's carbon neutral. That's the idea. That's the important point. The other thing about biofuels is that they're renewable, sustainable if you like, because you can just grow more of it. Whereas fossil fuels, of course, can't be replaced in our lifetime, so take a few million years to produce, right? So if you're using ethanol as a fuel, what you'll be doing essentially is burning it. So C2H5OH plus O2. The products of that are going to be carbon dioxide and water, just like burning any other hydrocarbon or any other organic molecule. So what I'm going to do is I'm going to pause the video and you're going to balance that equation yourself on the mini whiteboards. Rather than try to memorize this, you should be able to work it out in the exam. So feel free to check your answer. People battle with this one, and I'll show you why. So if you've got this wrong, what quite a lot of people will have done is miscount the oxygens. Just walk you through how I did it. So if you've got 2 carbons over here, you must have 2 CO2s. If you've got 6 hydrogens over here, you must have 3 waters. So you tot up the oxygens on the right hand side. It's 1, 2, 3, 4, 5, 6, 7. And so what people often do is they put 3.5 oxygens there, but look, there's already 1 there. So it's simply 3 oxygens on the left. I think you've got 3.5, haven't you? That's just not right then. It's just wrong, I'm afraid. Yeah, so that's the balance. You need 2 carbon dioxides, not just 1.
Oh, it's because I rubbed that out. So
Okay, that's fine. Right, so there we go. That's the balanced equation. That's one of the uses of ethanol. Probably the main use of ethanol that we need to be aware of. The combustion, the fact it's a biofuel, is really significant. The other use for it is that it's used a lot as solvents, often forgotten, and hand sanitizer. But the solvent idea is quite important. You've probably heard of meths, not meth, but meths, methylated spirits, which is mostly ethanol, but it's also got in it methanol, which is really, really toxic. I mean, incredibly toxic, and it makes you blind and kills you pretty quickly. So they make methylated spirits. They put a very strong smelling chemical in it to put people off drinking it, but also a very strong purple dye, again to put people off drinking it, because it's really quite bad for you. But methanol and ethanol are good solvents, right? Solvents. So things like dissolve. Let's say there's some ink stains on the floor where people have spilt it. They can get stuff like that off. So it makes a really good solvent. So if we get permanent marker on something, you can wash it off with methanol, or methylated spirits, or that sort of thing. Okay, but lots of other uses in chemistry as well. So you might remember doing chromatography with chlorophyll. Have you done that in biology? Chromatography, chlorophyll.
I think so, yeah.
So if you did, you would have used ethanol as the solvent instead of water there. Okay, right. Another reaction you need to know, I can't for the life of me think why they want you to know this, but it's required. So I might have even asked if I can do this one, but we'll see. So the next one is reaction with sodium. And if you look at it really carefully, it's really similar to the reaction with water. See how if I cover up that bit of the molecule, you see how it looks really a lot like water. Instead of the H there, we've got just a carbon chain. So it behaves very, very similarly to water. So what's the gas that's produced if you chuck sodium into water? Shout it out. In 3, 2, 1. Hydrogen. Yeah, that's why it catches fire, doesn't it? The potassium. So this is identical reaction in that sense. So you chuck sodium into ethanol, you get hydrogen produced, right? And that's from that hydrogen there. So if you look at it, to make 2 hydrogen atoms, to make a hydrogen molecule, you need 2 of these. So we put a 2 there. And all that happens is essentially that the hydrogen and the sodium swap places, just like in the reaction with water. So the other thing you get is this.
Is there a catalyst for this reaction?
Nope, you chuck it in and it works. And you get something called sodium ethoxide. So 2 sodium ethoxide molecules. I'm going to draw that for you underneath so that you see it in a different way. This is one of those, sometimes there's bits in this GCSE course which are kind of 1 or 2 markers and they're just kind of out there as ideas, but if you want to get the top marks, that's what you've got to be able to do, these sort of little details, learn these little extra details. So the reaction with sodium is that. Yeah. But you can, or if you think of it as just this, with the hydrogen falling off to make H2, and then the sodium in its place. But this is an ionic bond rather than a covalent, so we don't draw a line, we draw a minus plus bond there. But all you need to know is if it's like that, that's okay. Even without the plus minus, you'd be okay there. And you should know that this is strongly alkaline. So this is a way of making a base, so strongly alkaline. Sodium ethoxide, you put that into water, it's strongly alkaline. Right. Bit of a random one. And of course, if you're producing a gas, it will fizz. Unsurprisingly. Right, so there's one other reaction of. Are we okay? Can I move on, or we're still going? Just give me a wave if you still need that up. Right. So there's another reaction we need to know, which is one that you'll know already, but you don't know that you know it. So if I were to take a bottle of wine and pour a glass of white wine out, and then I forget that I've got it, or I don't feel like drinking it, and I leave it for a day or 2 in the kitchen, out in the air. I don't know how many of you have had a sip of wine, but wine is quite nice when it's fresh, but it's not very nice after a few days. So what sort of taste might it have in a few days? Anyone know what sort of taste wine has if you leave it, yeah? I'm not sure I'd use the word bitter, I'd say more sour, right? They don't know what might be produced if you take the ethanol. The clue is the name. Probably wouldn't be surprised if you don't know this at all. But what's going on is an oxidation process. So that little symbol there of an O in square brackets, I don't think you've seen before, but that's just a way of writing oxidation. Have you seen it before? Don't think you've seen it before, no? Anyone seen it before? So what you get is a chemical called ethanoic acid, which you have heard of before, right? Ethanoic acid, which is in what? Where do you find that in the kitchen? Ethanoic acid in what? No, not soap. No, vinegar. Yeah. So sour. Ethanoic acid. So you leave the ethanol out for a while in the conditions of wine where it's got some bacteria in there that kind of help the process along a little bit. But you get ethanoic acid. You do need to be able to write the full equation, which will involve production of water as well. So please write that full equation there. But this ain't balanced yet. You should be looking at every equation going, is that balanced or not? What's not right about that equation? We need another oxygen. All we do is we stick a 2 there. Okay, and I'll just explain to you what's happened in this process in a sec. Right. I'll just wait for everyone to finish writing. So what's happened there is that these two hydrogens, this one and this one, have ended up in the making water using one of the oxygens, okay? And the other oxygen has ended up here. So if the two oxygens that have been added, one's here. These two oxygens, one of them is here and the other one's here. So you can see what's kind of gone on there, right? So ethanoic acid plus water. So that equation you're expected to know. You can do that in the lab. That's something you might want to do in the lab with other oxidizing agents, but you don't need to know what they are. So you can do this in the lab, or you can do it just by leaving a bit of wine open, right? So it gives you a vinegary taste. Vinegar. All right. So there is an experiment I want to do. We're not going to do it today, unfortunately, because we'll do a little bit of something else at the end of the lesson. But burning alcohols is an experiment we'll look at. But if you take any of the alcohols, so CH3OH, which is methanol, C2H5OH, which is ethanol, C3H7OH, which is propanol, and the pattern goes on. If you combine them with oxygen and you heat them, and they catch fire, you'll end up getting carbon dioxide and water in each case. And we're going to just balance, so go ahead and balance all of these equations. You might see some patterns starting to form there. So 1, 2, 3, 4. So 1, 2, 3, 4. We've got one already. So 1.5 oxygens. 1, 2, 3, 4, 5, 6, 7. So 3 oxygens. 6, 7, 8, 9, 10. Got one already. So 4.5 oxygens. Now this is. I'll give you a chance to write that down.
Oh, well, we're not supposed to write butanol.
Well, if you've done it, it's no harm. It's the same pattern follows. All right. So what's going on here is that in each case, the carbons have been oxidized to carbon dioxide and the hydrogen's oxidized to water. That's always the same with combustion, right? But look at the ratios of the alcohol to oxygen. the ratio is 1 to 1.5, 1 to 3, 1 to 4.5, and up it goes. So in order to undergo complete combustion, you need way, way, way more oxygen for propanol than you do for methanol, right? Which means it's much less likely that you're going to get complete combustion for the longer chain alcohols, or indeed longer chain hydrocarbons, because the amount of oxygen you need per molecule is much, much higher. So these ones are more likely to undergo incomplete combustion which means you tend to get a more smoky flame. You tend to get a more yellow flame, which is the soot. Yellow, all yellow is glowing soot. As you go that way, you're more likely to undergo incomplete combustion because you need more oxygen. More oxygen is required per molecule. Conversely, though, the longer the chain, the more molecules of carbon dioxide you get out, which means they release tons more energy as well. So the flame's also hotter, but more energy released, more per molecule. And you get, I think we talked about this with hydrocarbons, the long chain hydrocarbons. You're often used in very, very powerful engines like power stations and things like that. Okay, right. That's what we need to know for the alcohols. So I'm going to stop the video there, and we'll do some other bits and pieces.